Hey everybody, Mike Barr, old electrical safety guy here. Just want to take a couple of minutes and talk personal protective grounding. I'm going to set up an incident on my simulator back here and kind of try to demonstrate some of the issues that we continue to see out there in the with our line workers. and It's just one of the areas where we continue to see fatal accidents and injuries involving our line workers. I think there's a couple reasons for it. Obviously, complacency is one of them. Back in, I first learned about personal protective grounding, or at least the concept of EPZ, or single point, equipotential grounding. I first started hearing about that back in I would say the mid 70s, before it was an OSHA requirement, before it was really that much of a practice. Prior to that, when we did ground, most of us were taught and believed that bracket grounding was the safest way to go. And I still encounter a lot of pushback when it comes to EPZ. When we talk about bracket grounding versus single point grounding, in that, I have a lot of guys kind of challenge me and say, Mike, I've been doing this for 30, 35, 40 years, and man, I've never seen an incident. So the bracket grounding must work. Well, yes and no. All that really means to me is that the person that was exposed, the conditions for that induced voltage that needs to be present on that line, and then having the opportunity to be across two different potentials at the same time, with a difference of potential high enough, in other words, greater than 50 volts, to cause a problem for that person. It doesn't necessarily mean that he was protected. Now, obviously, bracket grounding is more protection than no grounding at all, particularly when it comes to a line being accidentally energized. Which is extremely rare. Doesn't happen often. I'm not going to say that it hasn't happened and won't happen and can't happen, but it's really rare. And when we think about a line becoming energized accidentally and then killing or injuring someone, you got to think about the window. The window for that hazard to exist is extremely small. It is a very short period of time, and one thing, especially on T-line, you would have to put yourself in some kind of a parallel path or in series with that current at that exact moment that circuit becomes re-energized, and so your window is very, very small. One is the likelihood of someone closing that line while you're on it and exposed is really, really remote. And then if it does happen, the time period that you're exposed is very, very brief, very short. So it's not something that, frankly, I have been able to find much in the way of injury or fatality, if any, when it comes to line workers being killed or injured during an accidental re-energization. So it's rare, and again, I'm not going to say it can or won't happen. But the problem is with the induced voltages, because now your window of exposure is there's no limit to it really. As long as that induced voltage is there, then you're exposed, and so we're seeing more and more of this as our corridors get more crowded, and we get more people working on those lines, and those induced voltage hazards are increasing. And so because of the numbers that are working and the exposures, we're seeing more of this. It just continues to happen. So anyway, that's what I want to talk a little bit about today. And what I try to do, of course, when I teach my classes is I try to get people to think about themselves as being part of an electrical circuit, and try to think electrically instead of mechanically. Because when we got guys out there thinking mechanically, and you see a sign, somewhere, or a bumper sticker that says if it's not grounded, it's not dead, and they see a set of grounds up in the air, then they think they're good to go, which just, isn't necessarily the case. So we got to get people thinking a little bit different about it and understanding some of these principles of current flow. Current flow in a grounded system, it's going to flow in a grounded system the same way it flows in an ungrounded circuit. Current in a parallel path it's going to take every path available, and of course that current's going to be inversely proportional to the resistance of the path. So that means that all interconnected systems will have current in every path. And of course the low resistance paths are going to have more current flow than the higher resistance paths. So, but remember, we only can withstand a very, very small amount of current before we get into trouble. So remember, we gotta make sure people understand that multiple paths will have current flow. Every path will have current flow, and that current flow is going to be based on the resistance of the path. And not only that, that the voltage across all the branches will have the same voltage. The voltage drop across parallel paths is, of course, equal. So it's going to be the same across all these paths. And so, if you can't quantify it, you got to assume it's deadly and protect yourself. You can't make assumptions. We have to treat de-energized systems, our T-lines and our work in our substations and, of course, distribution. We can't make assumptions that on the level of induction. So we need to create these areas of equal potential no matter where we're working. And, studies have shown that under the right conditions, it only takes about 50 volts to break the resistance of your skin. And so that's the voltage level that OSHA has told us that if we are exposed to anything great at 50 volts or greater, we've got to protect ourselves from it. And there's many ways that we do that. Doing electrical work, we'll put gloves on, or we put sleeves on, we use line hose, we use hot sticks, insulated tools. And so anything 50 volts or greater, we have to protect ourselves from that. And that's because it only takes a few milliamps, less than 1/1000th of an amp, to cause our heart to go into fibrillation. And Charles Danzel, and others did some experiments back in the 50s and 60s, and they showed us that basically 155-pound lineman could withstand 91 milliamps for 3 seconds before they went into fibrillation. So very, very small amount of current. And obviously, if the current flow is higher than that 3-second interval will decrease. So it can happen pretty much instantaneously depending on the amount of current. So what I want to talk about today mainly, and again, I'll move back to my model here in a second, is that when we install grounds to de-energize the system, in the event that it becomes inadvertently energized, that will not protect the worker who is not at equal potential with that system path. So, grounds installed to trip the circuit, or tripping grounds, what I usually refer to them as tripping grounds, that's all they're for. that those are just there to meet one of the two requirements of the grounding requirements, and that's to trip the circuit. So they will not protect the worker at that work zone. We have to bond at that work zone to keep that potential difference between two different conductive surfaces as low as possible. We'd like it to be 0, but if we can get it below 50, then we're doing okay. So anyway, as I said, we rarely hear about someone closing on a grounded line. It just doesn't happen. In construction, the more likely scenario is if you're pulling, if you're sagging, and you lose a conductor, and maybe it results in those new conductors falling into an energized line. And if that happens, we should have set up some travelers that are going to do their job and trip that. But that still doesn't protect those that are on the ground and maybe in contact with the pullers and the towers and other conductive objects and rail trailers and things like that. We've got to still create that equipotential zone for those situations. And so what I want to do, I'm going to step back here to my model and just take a second and talk about this principle. I've already got this kind of set up, and what I've got here is, and this was an actual incident that happened a few years ago. We've got a T-line, and what happened is the top of that pole, about maybe a foot or two below where that static was attached, broke. And so they sent a crew out there to make some repairs, and I think what they were basically going to do is reattach that static below where that pole broke. And so they went out, they set up, and now they were utilizing a boom that was had no insulation. There was no insulated insert in the boom. And so they're working out of the basket, 2 men in the basket. But what they did before they got up there and attempted to do this, they went out and they put a ground on each side of the workplace. They grounded, they bonded their static that they were going to be working on into their grounds, okay? And so what they did is they established this bracket ground around them. They go and they set their truck up, and they attach a ground to the truck to a driven ground rod, okay? So what they've basically done is they've established a different ground source than what their bracket grounds. They bonded their bracket grounds to the static, okay, to establish their ground source. And then they attached their truck at the bottom to a driven ground rod, and of course, that's a different ground source, which means that there's going to be a difference of potential between the grounds that they attach their bracket grounds to, or their tripping grounds, or whatever they want to refer to them as, but it's two different ground sources. So what the guys do is they come out here and they get their basket, and the guy has got one hand on the rail of that basket, and he reaches out and he touches the static. And when he does that, as you can see, I hope you can see, that light up. When he does that, he slumps in the bucket, and he did not recover. It was a fatal incident. So now there's a couple things they could have done. The easiest way for them to prevent that would have been to take a bond and bond from the basket, okay? Bond from the basket to their neutral, and that now would have put that basket and the man at the same potential as as that static, and there would not have been any current flow, and that would have prevented this fatality. This is really common. Most of these accidents that we're seeing out there, and we'll talk more about these. I'm going to try to recreate, these things as I, every couple weeks I'll try to do a new one. But I have no doubt that these guys thought that they were totally safe. You've got bracket grounds; they got a ground on each side of them, and that static, of course, is bonded into those grounds that they put up. And every structure is bonded to ground. So I have no doubt that they really did think that they was perfectly safe. That working on that static was not going to be a problem for them. And so, guys, that's what I'm talking about when I refer to trying to get our people to think about being part of an electrical circuit. Let's get them thinking electrically and not mechanically. And to make sure that when they go out on a job that they're looking at everything and they're making sure that their hands, their feet, their bodies, their equipment, anything that they can touch is electrically bonded together, so that we don't have these differences of potential, because it's deadly, and we're losing line workers this way. So, and it doesn't have to happen. It's so easy. They could have used a number 14 copper wire from that basket to the static, and to equalize the potential between those two surfaces, and they would have been perfectly fine. So anyway, hope you like my latest rant, and let me know one way or the other whether this content is good or not. I tend to rant a little bit, and I'm not the, I don't have all the answers, but gosh, we gotta come together and start preventing this stuff. And appreciate your time, and thanks a lot.